Hi, this is an update on the status of the Tangerine SDR GPS disciplined oscillator clock module. The clock module for the Tangerine SDR has to provide accurate and stable sources of several signals as shown here. A GPS disciplined oscillator is the best way to accomplish both the accuracy and the stability that we need. We generate a number of frequencies, both at RF for the receiver and transmitter, and a pulse per second used for time stamping. And we also wanted to make sure that this system could be used separately from the Tangerine SDR because we think that the time nuts may be interested in a number of its capabilities. So just as a quick refresher, a GPS disciplined oscillator takes advantage of the fact that the GPS pulse per second signal you can get from many receivers is noisy. It has a lot of jitter in the short term, but in the long run, it tracks the atomic clocks at the US Naval Observatory and the National Institute of Standards and Technology. Whereas a crystal oscillator is very stable in the short term. It doesn't have much jitter, but over time it drifts and jumps around. A GPS disciplined oscillator tries to get the best of both worlds by using a phase lock loop to steer the crystal oscillator with the GPS. This chart on the right shows how this works. This is an Allen deviation plot. You can think of Allen deviation as sort of like standard deviation, although technically it's not. The x-axis is time logarithmically from 1 second to 100,000 seconds. The y-axis is fractional frequency difference. It's a version of parts per million or percentage. The lower on the y-axis you are, the better for performance. For its higher stability, low on the chart. As we look at this, the blue line is the pulse per second output from a traditional good quality GPS. The violet line is a temperature compensated crystal oscillator, and the green line is an inexpensive eBay oven oscillator. You can see that the GPS signal just keeps getting better over time. That's because the noise is averaged out and we get closer to the atomic clock performance. Whereas the crystal oscillators both are sort of flat at short term, but then they start to trend upwards as drift and other factors enter in. The idea behind the GPS-DO was to have a bandwidth of the phase lock loop to catch these crossing points. And have the control essentially transition from crystal to GPS at the crossover. You can see with a low quality oscillator, the crossover happens at a shorter time interval. This is about 15 seconds. With a higher quality oscillator, the crossover happens later, and you need a much narrower loop bandwidth to take advantage of that. This is a diagram of the Mark I clock module that I was working on last year. I won't spend any more time on this other than to say that it's complicated and it had an FPGA, which means lots of ugly programming. After working on that, I was working on some tests on some modern U-Blox GPS receivers, and we learned about maybe a simpler way to do things. The U-Blox receivers have a time pulse output that's normally set to PPS, 1 pulse per second, but it can actually be programmed to more than 10 megahertz on these modules. The output of the time pulse at RF frequencies like 10 megahertz is remarkably good. It's actually much better than the pulse per second output, but there's a lot of jitter on the 10 megahertz signal. Its phase noise sucks, and you'd never be able to put that signal on the air because it would just be too ugly. But separately, I learned that there is a series of chips manufactured, I think mainly for the telecom industry, that are called jitter attenuators. And they're designed to be used as part of the clock distribution system in large digital systems. Basically, you have one master clock that's driving a whole bunch of boards, and each board needs to generate its own clock frequencies and needs to clean up all the noise that's on the master clock signal after it's bouncing around the room. And these jitter attenuator chips do that. They have an external oscillator of their own that's used to provide the short-term stability and the phase noise of the output while being locked to the reference signal that's coming in from the external clock. So you actually have a phase lock loop, and it works a little bit like a GPS-DO might. The chips provide multiple outputs at anything from 100 kilohertz to over a gigahertz, and there are several outputs available depending on which chip you're using. So based on those ideas, we started from scratch with the Mark II clock module. We're going to use a U-Blox GPS time pulse at 10 megahertz that's fed as the input signal to a Silicon Labs 5345 jitter attenuator chip. And the PLL in that chip is actually acting like a GPSDO. The output of the chip is synthesized to the frequency we want, and that's locked to the 10 megahertz input, but its phase noise is significantly cleaned up. And the 5345 chip is great. It's got 10 independent outputs, and it can directly provide all the Tangerine SDR clocks, plus a whole bunch left over to use for other things if we want. This is a block diagram of the Mark II system, and you can see it's way simpler. Just a GPS feeding the 5345 chip, the outputs of the 5345 going to an interface connector, along with the pulse per second from the GPS, and also the serial data stream from the GPS, so that are all made available to the other side of the bus. This is the Allen deviation stability performance of the 10 megahertz output from 3 different U-Blox receivers. The blue is the cheapest unit, which is less than $20. The violet is the last generation timing receiver that's probably $60 to $70 today. And the green is the current generation receiver, which has a lot of new features. And it's about $150. You can see that the more you pay, the better performance you get. So things are working as we might expect. We're going to make the clock module available with any of these 3 options installed. So it'll sort of be a bronze, silver, and gold, depending on how much you want to spend for the module. We fed the 10 megahertz output from the best quality of those receivers, the current generation timing receiver, into the Silicon Labs chip evaluation boards. And actually, I have two of those boards. One is for the 5335 series chips. The other is for the last generation 5328. The reason for that is that the evaluation board that's available for the older generation chip has a temperature compensated crystal oscillator, but the evaluation board for the current generation chip is just a bare crystal oscillator. We want to use a TCXO in our design. So the performance of the 5328 evaluation board with the TCXO is significantly better than the more modern board, but with just the bare crystal. The top 2 lines are the bare crystal, the blue and the green at 2 different loop bandwidths. The bottom 2 lines, the red and the violet, are with the TCXO on the older chip. And you can see the significantly better performance that we get with the TCXO. Now, the trade-offs of this design are these. On the Pro side, it's much simpler. There's no FPGA programming required, and the cost of the non-GPS components is much less. So that makes it less painful to use a better quality GPS module. And it gives us huge frequency agility with 10 outputs and any kind of frequency we want, basically from 100 kilohertz to a gigahertz. The con side is that the crystal oscillator that's used by the chip is in the 40 to 50 megahertz range, and it's quite difficult to find a wide range of choices of TCXOs or oven-controlled oscillators at that frequency, and they're significantly more expensive. So we don't have a lot of choice in the oscillators we can use to improve performance. And also, the jitter attenuator chip, PLL, has a loop bandwidth that goes out to about 1/10 of a hertz or somewhat less than that. And that's fine for moderate performance, but if we had a very high quality oven oscillator, we wouldn't be able to get a long enough loop time constant to get the maximum performance. So this design is not really capable of laboratory performance, but the performance that we're seeing is more than enough for the HF RF applications that we're targeting right now. There's also an issue with the fact that this design relies on the pulse per second signal that's coming directly from the GPS module for the timing side of the system. If the GPS signal is lost, the pulse per second goes haywire almost instantly. So it doesn't really have a holdover capability. And synchronizing to the pulse per second as more complicated. We can work around this in the FPGA of the data engine. So it's not a serious problem, but it is something that we need to take into account, and it does complicate things a little bit. We think, though, that that trade-off is worthwhile for all the other benefits that we get. So the status as of right now is that I'm still trying to finish the proof of concept. I really want to get a TCXO plugged into the 5340X evaluation board. But even if we're not able to do that, the separate testing we've done gives me a very high degree of confidence that this is going to work the way we expect it will. The schematic design is basically finished at my end, and I've turned it over to Scotty, who's pouring it into his CAD system. And from that, we'll generate the final schematic and start doing the board layout, which we hope will begin fairly shortly. My next project, now that this is finished, is to work on the carrier board for the Time Nuts crowd. So I'll be starting that design shortly. And that's about it. Thanks.